Cast titanium. Falcon 9's Block 5 booster relies on massive, single-piece cast titanium grid fins. Titanium offers the perfect strength-to-weight ratio to survive the hypersonic, glowing heat of re-entry. But casting titanium parts of this size is a manufacturing bottleneck. Historically, the global raw titanium sponge market was dominated by a single geopolitical wildcard: Russia. SpaceX had to transition its primary metal mills domestically, relying on high-end U.S. suppliers. There is no easy detour for the Falcon 9 grid fins. However, SpaceX solved this on their next-generation Starship by executing a massive design bypass, switching the fins entirely to welded stainless steel. High-tensile carbon fiber. Carbon fiber is the busiest structural axis of the modern rocket. Connecting carbon composites to the sky, it is used for Falcon 9's payload fairings, interstage, and Dragon spacecraft. SpaceX relies heavily on ultra-high-grade carbon fiber sourced from Japan's Toray Industries. Because this material has military-grade strength, the supply line is highly regulated, navigating a minefield of international trade laws. The physical limit is the curing process. Weaving and baking carbon composite fairings takes massive, expensive autoclaves. That is why for Starship, SpaceX executed their most famous material detour, abandoning carbon fiber completely to build the giant rocket out of basic, cheap stainless steel. Specialty Inconel powders. To build the high-pressure turbopumps of the Raptor engine, SpaceX uses advanced metal 3D printing. The ink for these printers is Inconel, a superalloy that handles extreme thermal stress. But Inconel isn't a single raw metal, it's a highly regulated cocktail of nickel, chromium, and cobalt. Sourcing these precursor metals drags SpaceX into the deep, volatile mines of Central Africa and processing hubs in China. It is a highly regulated channel. If any single ingredient is blocked by sanctions or export bans, the 3D printers at Hawthorne stop cold. Liquid helium. Keeping liquid propellants pressurized during flight is a silent engineering nightmare. To do this, Falcon 9 carries several high-pressure bottles filled with helium gas, submerged inside the ultra-cold liquid oxygen tanks. But helium is extremely rare, incredibly expensive, and a logistical headache to ship. It must be kept at a frigid 4 Kelvin, just above absolute zero, to be transported in specialized cryogenic ISO containers. Because the U.S. is highly dependent on a volatile, fluctuating helium supply, every launch requires careful coordination. The bypass? Autogenous pressurization on Starship, which eliminates helium entirely by using the rocket's own vaporized propellants. Autogenous pressurization. When shortcut materials like helium are too risky or expensive, you have to take the long, difficult route. On Starship, SpaceX uses autogenous pressurization by routing liquid methane and oxygen through the engine's heat exchangers, vaporizing them, and piping them back into the main tanks. The rocket pressurizes itself. This eliminates the helium supply chain entirely. It is a massive, highly complex thermodynamic detour. It requires months of engineering and adds structural weight, but it is the ultimate backup plan that keeps SpaceX independent from the global helium crisis. Krypton and argon. SpaceX doesn't just build rockets, they mass-produce satellites. To keep thousands of Starlink satellites in orbit, they use electric Hall effect thrusters. Traditionally, these thrusters run on xenon, an incredibly rare and expensive gas. To keep costs low, SpaceX designed their V1 satellites to run on krypton. But there was a bottleneck. Ukraine historically produced up to half of the world's purified noble gases as a byproduct of steel manufacturing. When geopolitical conflict shut down Ukrainian steel mills, the supply vanished overnight. The detour? SpaceX redesigned their V2 satellites to run on argon, a gas that makes up 1% of Earth's atmosphere, making it cheaper and infinitely more abundant, but far harder to ionize. Aluminium-lithium alloys. To contain the immense pressure of cryogenic propellants, Falcon 9's massive propellant tanks are made of aluminium-lithium alloy. Adding lithium to aluminum dramatically increases strength while reducing weight. But this alloy requires ultra-pure lithium imports from Australia and the South American lithium triangle. These raw ores must be shipped to highly specialized domestic mills to be rolled into precise aerospace-grade sheets. Because there are very few mills in the world capable of producing this specific alloy to SpaceX's standards, any disruption in the domestic metal processing sector acts as a direct gatekeeper to the launch pad. Silicon and E-band transceivers. Mass-producing thousands of Starlink terminals a day requires specialized high-frequency semiconductors, specifically gallium nitride E-band transceivers. SpaceX depends heavily on high-tech foundries. If this semiconductor pipeline is disrupted by global chip shortages or geopolitical tension, the Starlink assembly line, which brings in the majority of SpaceX's long-term revenue, grinds to an immediate halt. Stainless steel. While Falcon 9 relied on complex composites, Starship shifted to 304L stainless steel. This material choice is unconventional for modern aerospace, but offers extreme thermal resistance. Stainless steel is incredibly cheap compared to carbon fiber, allowing for rapid iteration and mass production. The challenge is weight. Steel is heavy, requiring SpaceX to push the limits of material thickness. Sourcing massive quantities of high-quality industrial steel requires leveraging domestic U.S. steel mills. It eliminates the need for expensive autoclaves and clean room environments. By choosing basic steel, SpaceX trades material complexity for manufacturing speed and cost efficiency. Ceramic heat shield tiles. To survive atmospheric re-entry, Starship uses thousands of ceramic silica tiles. These tiles act as an ablative thermal protection system to manage intense heat loads. Manufacturing these tiles is a precise, time-consuming process involving specialized kilns. Each tile must be perfectly shaped and attached, creating a massive logistical and labor hurdle. If the tiles are not perfectly bonded, vibration during launch can cause them to fall off, creating hotspots. This represents a brute force engineering solution, managing heat through massive quantity and precise placement. The supply chain for high-purity silica raw materials is crucial to keeping the Starship assembly line moving. Liquid methane. The Raptor engine requires liquid methane, a shift from the kerosene, RP1, used in Falcon 9. Methane is cleaner burning, which is essential for rapid reusability and engine longevity. Sourcing high-purity aerospace-grade methane is a significant infrastructure undertaking. Unlike RP1, which is a refined petroleum product, methane is extracted from natural gas. SpaceX must partner with local cryogenic facilities to ensure a steady, high-volume supply at the launch site. This propellant choice makes refilling on other planets, like Mars, theoretically possible via Sabatier processes. It turns the fuel supply chain from a commodity purchase into an on-site generation requirement. Solar array photovoltaics. Every Starlink satellite requires massive power to run its transceivers and ion thrusters. SpaceX manufactures these solar arrays internally to control costs and supply stability. The reliance is on high-efficiency silicon wafers and specialized thin-film coatings. These materials must survive the harsh, radioactive environment of space for years. Similar to the transceivers, this supply chain is global, relying on specialized semiconductor manufacturing. Any bottleneck in the global supply of high-grade solar materials directly threatens the Starlink deployment cadence. By vertically integrating this manufacturing, SpaceX secures its own power generation capabilities for orbit.